Yay. Okay, great. Okay, so it's 3 real talks and like 0.1 kind of review, and it's based on the 3 main ones are based on 3 things that we just presented at a conference just before this meeting. Okay, so this one, if for those of you that did go to my talk last time, I did talk about it, but it fits in the theme, so I thought I would just mention it again. And if you want details, talk to me after. So this is the only thing in this talk that was actually based on a real animal. So we had data from Drosophila, and we wanted to make an interpretable model that reproduces the 3D joint kinematics of the leg movements of the Drosophila, that keeps producing these patterns even if you poke the legs. And then we wanted to look at how changing sensorimotor delays in that model would change the walking. And we did that using a layered architecture. So I'll just briefly mention what's going on here. So at the very, very bottom, we have a dynamics model.
Can I make a timed request?
Oh, yes, cursor.
Use your mouse.
Okay. So at the very bottom, we have the dynamics model, which is the leg of each.
Just look at your laptop.
Okay. Which is the leg. And then, okay, so which one shall we start with? Let's start with this one. Okay, so the trajectory generator, this is just a very vanilla neural net, and we trained it on kinematic data from the flies. Okay, so if you train it and it has enough parameters, it's gonna fit it, which is good. It reproduces the kinematics as you want. So that was one of the things we wanted to do. However, if you start perturbing this as it's generating trajectories, it's gonna do really weird things. So that's where the layers come in. So we use this controller, and actually doesn't matter too much what it does as long as it tracks. It has good tracking behavior. It tracks the trajectory made by the trajectory generator, and that lets us keep producing these trajectories even when you perturb it. So when you kind of poke the leg, the controller handles the poke. It rejects the disturbance for you, and then you can keep, maintaining a relatively regular pattern. And then we did this additional thing where we kind of put delays into the controller. And so you could say, oh, I want a controller with like 30 milliseconds of actuation delay and 10 milliseconds of sensory delay, pop it into this framework and then have it walk. And then you can say, okay, I changed my mind. Now I want to have 20 milliseconds of delay each, make a new controller, pop it into the framework, and then do it all over again. Okay. Yeah.
What's the problem with just having the trajectory generator? What do you say? What do you mean it does something weird?
So like, let's say your trajectory, let's say one of your joint angles is normally doing a sinusoidal wave like this. Now, if you add a perturbation or a delay and then keep using the trajectory, it's going to do like that. And then it's going to keep going.
Oh, okay.
Well, I mean, it does get back. Well, sometimes it goes on, and sometimes it gets back. But this is, it's like, 20 degrees and then like 200 degrees and then back, and it's not right. Whereas if you do the same thing with the controller, you just get a little blip and then you'll come back. So yeah. Okay. And then the 6, so there's one of these things on each of the legs. So we have 6 of these little stacks, one on each leg, and then they're coupled through a coupled oscillator. Just one idea of how to do kind of layered control. Again, I'm not going to talk about it because I actually talked about it a lot last time. And here's a nice video of our model. Let's see. Sorry. Yeah, okay, so the one on the left is the data and the one on the right is the model. Okay. This is without perturbations. And then we have a bunch of stuff in the paper with perturbations. Okay, that's the mini talk. Now we'll start doing actual math. Okay, so the first thing we're going to talk about is bipedal balance. So this was done by 2. So these 2 were undergrads at University of Michigan at the time, which explains a lot of the design choices that you're about to see. But they're both going to institutions to do their PhD. Okay, so we were in a topics class, and we wanted to model some type of behavior with a controller. Now, the vanilla version would be to model like a person balancing on a flat ground using inverted pendulum models. Is fairly straightforward. But for some reason, these 2 decided that they wanted to make the person balance on a log instead. So you can see it's a circular cylindrical object that you're trying to stand on. Okay, so let me say this. So the assumption is that you cannot slip off the log, so you have enough friction that all you're doing is this on the log with your foot, and then we allow it to move both the ankle and the hip joints. And this is because if you use a single inverted pendulum model and you only allow it to move the ankle, then you basically can't balance that well. You can only balance well if no one's poking you. So we wanted to be able to balance if someone pokes us. So that's why we gotta add that.
Log rolling like these guys do in these loggers do.
No, that would have been the next step if they stayed on. Yeah. Okay. So so imagine that the log is like fixed in place. I'm sure there's plenty of logs here in Telered. We could try this on. Okay. We allow the controller to sense the joint angles. So that's like ankle, hip. I think there was one more. Okay. And then we also allow it to sense the center of mass and the x coordinate. That turned out to be really useful. And then we allow it to sense its derivatives. We have some equilibrium and try to restore to. So we're trying to restore to like 0 center of mass and then kind of just like standing upright. Okay. And then the controller takes that and then outputs either both ankle and hip torque. And then we did this all with like fully nonlinear body dynamics. This is a nice like chunk of equations in the paper. Okay. So how did we manage to do this? So it turns out that you can balance pretty well using a modular, aka layered, switched approach, and you can do this all using simple controllers. And again, part of the reason was that these are undergrads that didn't know that much about complicated controllers, so they said, we just want to put a bunch of simple controllers together. And it turns out that that's enough to balance pretty well. Okay, so the first thing to notice is that you have to separate the operating regime into a couple of different cases because you don't want to be using the same controller for different scenarios. So here are the 3 scenarios that my undergrads found, I think, by repeatedly trying to do the task themselves and thinking what strategies they use. No, but it's a good set of control. Okay, so the first case is the easiest case. This is a case my torso is upright, like I'm in a good posture. My center of mass is close to the center, so I'm balanced. So I'm balanced and natural. So this is good. This is the goal. When you're in this case, like it's not that difficult to balance, and you can do this with like probably one simple controller. Okay. This is not the fun one. So now you're balancing and your friend comes and like kicks you or something. And now, so your torso might still be upright. I don't know what, depending on how you get kicked. But the main problem is that your center of mass is going to be far from the center if you receive a perturbation. And now you're about to fall. And this is made worse by the fact that you're standing on this log that actually accelerates you if you're off balance. Okay, so what you need to do here is really, really quickly restore your center of mass. We don't care about posture right now. We just want to not slip off or fall off the log. And that leads to the third case. So the thing that they decided to counter center of mass deviation is you just throw your hip back really, really quickly, and that'll allow you to restore your center of mass really, really quickly. And now you're left in this very awkward position that you don't want to be in for a long time. So you'll slowly, slowly stand back up. Okay, assuming no one kicks you in the meantime. Okay, so these are the 3 cases. And then they developed a different controller for each case. So for the first case, this is the easy one. Sorry, the Zoom is blocking me. Okay, so the first case, this is the easy one. So we have a separate loop for the hip and for the ankle. In this one, the 2 controllers don't need to coordinate. So we just put a PD controller on the hip that makes it stiff. And then you can go back to kind of single inverted pendulum ideas. Now, even as a single inverted pendulum, the system's a little bit weird because of this like ankle on log motion. So it turns out that the center of mass and the x coordinate of the point of contact, they're affine with each other, as shown by this first equation. So what we do is, well, it's affine, so we throw it into a linear controller, so that's the linear quadratic regulator. And that one's going to tell you here's where your foot should be on the log. And then we translate that into the desired angle of the ankle, okay, right through this transformation, and then we give that to a PID controller to track the ankle angle. Sorry, I'm gonna say that a lot. The reason we use a PID to track and we just tune it is because the full dynamics are really annoying, and there's not that much benefit to writing them up analytically and trying to find it, so we just tune for tracking. Okay. So this one is decentralized. You can think of it as a reflex if you want. Okay, this is the boring one. Now let's do the fun ones. So, okay, so this is the case where you're about to fall. So now you're going to use one controller for both of the ankle and the hip. If you make some assumptions that I don't remember in the moment, but we can look at the paper, then again, you can write your center of mass. So this is why center of mass is important. Center of mass is actually sort of linearly related to a lot of the quantities. So in this case, the main thing we care about is putting the center of mass back, and that relates directly to the hip torque. So it's affine. Same story, throw it into the
Does
LQR.
that mean affine?
Sorry, affine is like linear plus another linear term. Actually, no, these are both linear.
With what?
No, these are both linear, actually. Sorry, my bad. Affine is a more general class. Yeah, yeah.
Okay.
So this is COM is linear with respect to tau2, right? The hip torque. Before it was COM is linear with respect to like a term of itself with a term of X contact. Yeah.
It's like an affine transformation in deep learning as that bicycle. Oh,
Okay.
X plus B. Yeah.
Yeah, it's AX plus BU, exactly. Okay, right, okay, so linear, do linear methods. Linear method's gonna tell you where it wants the center of mass to be. So your hip's gonna do some of that, and then you also want your ankle to cooperate. It's not that important what your ankle does, but you want it to kind of drive you to the same center of mass that the hip is trying to drive you to. Same story. So we take, oops, sorry, I guess I didn't write that equation. So you take the center of mass, and then you do some inverse trigonometric function on it. Again, you get a desired ankle angle, and then you track that with a PID. Okay. This is not so different from the third case. So the third case, the only difference is we kind of change our assumptions a little bit. So the second case, our assumptions are based on the fact that you're moving fast because you don't want to fall. The third case, you're not moving very fast anymore, so the contact point of the ankle becomes a little bit more relevant to your center of mass. So the second one, it's not so important that I get my center of mass back to a specific place. I just need to get it less, right? I just need to reduce it quickly. Whereas the third one, if you're moving your hip around, you're throwing around your center of mass. So you really need to compensate with your ankle so that you can stand back up without upsetting yourself physically. Okay, so again, linear. And then it's the same story. So we take the center of mass for case 3, we take the contact point again, we do the trig function on it, and then we get the ankle angle, and then we track that. So we use a lot of linear stuff in here, but what's kind of interesting to me is that they actually did not once linearize the system. So, okay. So now I have to kind of show a simulation, right? So here's let's see how I'm doing. Okay, so here's the different quads. So there's like center of mass here, there's foot angle, leg angle, torso angle, and then here's the 2 torques. From the 2 torques, you can see when this guy is getting kicked. So they got kicked 3 times. These are the 3 spikes. Okay, and then the color code is according to the case. What else do I want to say? Oh, these 2 lines. So remember, we do use a PID at that bottom layer to track. So these 2 lines are just showing that we do track it relatively well. Okay, so case 1 is like we're standing upright, all good, and then you receive your first kick. It was I think standard deviation 80 newtons and mean 50 newtons. My student loved to describe it as having a small watermelon thrown at you, but without considering the impact issue. It's just force-wise.
Pink border?
Yeah.
Blue pink border? Okay.
Yeah, oh, sorry. Where's my mouse? Here, like this is the first kick, right? So at the kick, now you're thrown off balance. So now you're in the pink color, right? Which is the case 2. And then see, case 2 finishes very fast because if you don't finish balancing yourself very fast, you're gonna fall. Okay, so then you throw your hip back, and then now you're in that like really awkward posture case. That's the green case. And then after a while, my mouse keeps disappearing. I'm sorry. After a while, it goes back into the blue case, right? So I'll like show the video, right? So here's the guy, he's standing, everything is good, and he gets poked. Okay, so he gets poked, and then now he's slowly restoring himself back to the upright position. Okay, they're upright enough. It went back to state 1, and they got kicked again. And now have to balance, and they got kicked. So they got kicked twice in rapid succession at the end there, but it was okay.
Is that force applied uniformly across the entire unit?
No. I think it was just applied at the hips. Your friend throws a watermelon at your hip, I think is what it is. Yeah.
Sure.
So we tried this with random. So we tried this like over 1,000 simulations with just random 3 kicks applied in the beginning, and we were able to balance about 85% of the time, which is like pretty good. I think that is probably on par with human performance. I can try it later, but okay. So that's this controller. I guess I can pause for questions. Yeah.
Yeah, so us as naive people would just say, look, this is a really complicated control problem. We don't know how to do all this stuff. We'll just write the ODEs of the system, and then we'll just use MPC with the stochastic solver.
You probably can. There's
You know, as long as you're not too far from equilibrium and you can.
The thing with your objective is gonna be slightly weird, like.
It's much more expensive, right?
No, but what I'm saying is like, let's say you're doing standard like deviation from equilibrium weights, right? So how heavily do you penalize that?
Yeah.
Because at different points you actually, so even for MPC, I think there would be benefit in using a switch case because like, if I'm really close to equilibrium, it doesn't matter as
It switches
much.
its own behavior automatically by the optimal control.
Yeah, this one, so basically, oh, I skipped the picture where so each of these is actually quantified by the state regime. So your controller will say like, current state is this, like I will do the case one controller, or current state is that, and I'll
You
do
have to
this.
decide that on the threshold.
Yeah, you have thresholds for that, yeah. So that requires a little bit too, yeah.
So it's hand tuned or?
That part is hand tuned, yeah. I don't think it's as sensitive to, it elicits different behaviors in the person, but within a certain range, like you're still able to balance. It's just that like sometimes your person will just spend a really long time like this, right? And sometimes your person is like really aggressively trying to stand back up. So if you go to the extremes, those will destabilize you. But like within a certain range, it's kind of almost just personal preference. Yeah, and you'll still be able to stand up.
One more question, isn't that center of mass privileged parameter? Or
It is. The center of mass, some other studies have used it. If you use center of mass, it allows you to use simpler controllers. This is true. There's also, I think it's a plausible quantity.
so it's not really.
I think it's a plausible quantity to be measured by the nervous system, that we have a good, at least estimate for it. Yeah. Okay. So this is the first mini talk. Now we have the second mini talk. The completely different project, has nothing to do with the guy on the log. Okay. So this is also done by my student. So we wanted to model quote unquote bimanual coordination, but the setting is very strange. So the setting that we have is your two hands are paddles in a pong game, and you're controlling both of them. So I'm gonna do this a lot during this talk. So like bimanual coordination is studied in various ways, and also the mechanism of attention, not as you know it in transformers, but just attention as in I'm looking back and forth at my hands. Okay.
Like juggling, right? A little bit like juggling.
Yeah. Yeah, actually this one, depending on how you do the math, it can generalize to juggling, but we didn't get that part. Okay, so it's a single player bimanual pong game, and we have a few objectives. So first we want to hit the ball. This is the basic one, right? You want to keep hitting the ball. The second one is that we want to minimize the control effort, and control effort here is just like how much you have to move your hand. Okay, you don't want to be like doing this. So the third one is we want to minimize the attention or visual processing. We're going to use a proxy measure for that, but that's generally what we mean. And then lastly, we want to coordinate between the hands, because how much one hand has to do, how much motor and attention effort depends on the other hand. Okay, and there's ways people have studied this, but the ways people study this is very much like, let's assume that they like have this fixed strategy for that one. Let's observe the other ones. And my student wanted to just throw everything into one optimization. So we did that. We built an optimal controller that does optimization over all of these things. And then we looked at the behavior. Okay. So here are the 4 objectives. And then, so this is the kind of architecture that we settled on. Again, layered, as you'll notice. So each paddle gets its kind of own controller, and then you have a coordinator that coordinates between the two of them. Okay, so let's talk about the top one first, the global coordinator. So that one is in charge of 2 of the objectives. So at each collision, the global coordinator solves a competing optimization problem for attention and coordination. So it's going to output some desired trajectory of how you're going to hit the ball. This matters for coordination because how the ball bounces off of the first paddle is dependent on the velocity that you hit it with. So if you hit it with a nice velocity, it's going to go to your other hand. If you hit it with a terrible velocity, it's going to go somewhere really far away. Okay, so it tells you the trajectory, but then it also tells you a time varying penalty, and that is how important is it for you to follow this trajectory? Okay, because to follow a very specific trajectory, you need to look at your hand and make sure that it's following the trajectory. If you don't care at all, you need no attention, right? Just let your hand do whatever. You don't need to look at it. So I'll give you the math for that.
Are you assuming
Yeah.
you kind of have to watch the paddle to control it? In other words, you don't
So here so we're just using a state penalty Q as like a proxy for attention. So we're saying higher Q likely requires more attention.
Okay.
And lower Q, 0Q would require no attention, right?
Q is control.
Q is the state penalty term. I think I'll have that in the next, yeah. So big Q is I care a lot if I deviate from my course. And small q is I don't care if I deviate from my course. Yeah. Yeah, okay, here, equation, great. Okay, so the second thing that we do are the local MPCs, and that takes care of the other two things. It rallies the ball, it literally hits the ball, and it also minimizes the control effort. So this equation here, this is just a standard like quadratic penalty optimization. So the x bar is our deviation from trajectory. So we have some terminal costs, but throughout the trajectory, right, at every time step in the trajectory, you care about like this quadratic term of q and x. And if the q is large there, that means I really want the x bar, the error, to be small. And if the q is small, then I don't care. Okay, and then this last term here is just a energy or control effort penalty term. Okay, we have to obey some dynamics. We start with the initial point.
What is R?
R is the penalty for the motor effort. So if I have a very large R, then I'm incentivized to make U very small, right? Which would decrease my motor effort. Good question. Okay. So yeah, we're very, very loose with the word attention. Just think of it as Q. Okay. So now we can look at the values of Q for different types of tasks. So the top one is a hard task where, like, from this hand's perspective, the ball is going somewhere that is not where it is. So it has to move to go get it. And the second one is the easy task where the ball is already coming towards you. And the attention values are over the horizon. So in the very beginning, the ball is far away from you. There's really no need to pay attention, whatever your trajectory is. Okay? So the upper layer will give you a trajectory, but in the beginning of the trajectory, when the ball's far away, it's going to say whatever, follow it if you want. Okay. As the ball starts approaching you, so that's as these values get higher and higher, the ball is coming closer to you, and now it becomes more important that you actually do follow the trajectory, because if you don't, then you're going to miss the ball.
But who computes that Q? Where is
This
that?
guy, global coordinator, the upper layer thing. I don't know if you can see.
Oh, I see. Okay.
Yeah. Yeah, so we don't put them all together in one lump because then the optimization will be super ugly. So, okay, so for the hard task, you pay more attention, and for the easy task, you pay a little less attention. Okay, so your attention value depends on what your other hand did. Right, so how difficult it is to get to the ball depends on the other pedal's trajectory. I think I have an issue. Oh, good, I have an image for this. Okay, so to make this a little bit more concrete, so let's say your ball is over here, you're about to hit it. Okay, so this is the right and this is the left. Okay, so if you say I'm lazy and I'm not going to coordinate at all, I'm just going to hit the ball and then move on with my life, then you're going to get to this no right effort. You didn't make an effort, right? So you just hit it and it bounced off wherever. Okay, you can say I'm feeling charitable today. I want to contribute to the cause. I'm going to move a little bit so that it makes the left pedals work easier. So you can kind of plan the velocity so that it bounces off at this middle angle better than the no effort case, right? Or you can really say, I really want to make the left paddle do nothing, so I'm going to hit it exactly to where it already is. Or you could go really crazy and say, I'm going to make a really bad trajectory and just hit it somewhere that the other paddle's not going to be able to catch. Okay, so, but the middle three kind of are the point here where you have this like attention versus coordination trade-off. You can say, I don't care, as long as I hit it, it's whatever, right? Or if you try to control your velocity with a little more precision, that'll affect how the other hand, it'll let the other hand use less effort. Okay. What else do I have? Simulations. Good. So this is the case with no coordination. So remember I talked all about this coordination, attention, effort. This one has no coordination. So I'm going to hit the ball and then move on with my life. And then, as you might imagine, you keep hitting the ball, but because you're not considering the other paddle's trajectory, you just keep moving. Okay, so this one is attention cost. So attention cost is going up because the ball keeps getting hit to something very far away from you, so you have to really track it to get there. This one is the change in vertical displacement between two collisions. So this one keeps changing, right? Like the vertical collision keeps occurring lower and lower and lower and down the graph. Okay. So this is just a sanity check. Now we have some slightly more fun case. I don't know. Okay, coordination. So your coordination, so basically that upper level controller is just solving a combination of the coordination and attention problem. And you can tune the weights, right? How much you care about attention, how much you care about coordination. So if you have, so we have weak and strong coordination. These are the two lines. For weak coordination, so you can see that the green line doesn't quite get to 0. So that means that the ball does keep drifting a little bit, and that causes you to also keep using a little bit more attention. Whereas for strong coordination, both of the values settle to 0. So you settle to this perfect place where you just do this, and then you don't have to move or see or anything. What do I have? This is the weak case, because you can see they're still kind of inching down at the very end. Okay. And then this is probably the last one, handedness. So we want to try this because everyone is handed. Most people are handed. And we encode this by just making the plant for the hand, so the dynamics for one hand move less well, so harder to move or more unstable. That means it's more difficult to track for that hand. So here, the displacement is the same across both hands, but the attention is different. So your left hand has to pay a lot of attention, has to make a lot of tracking effort, and your right hand doesn't have to do so much. So this is the case for right-handedness. And then if you make your left hand a little less bad, then the same trend still persists, but the values are a little bit lower, okay? And they actually do converge very, very slowly to 0. So according to our framework, we don't know if this is true, but according to our framework, if you're doing this and one of your hand is substantially worse than the other ones, you'll be paying more attention to that hand. All right, so here's this is the low asymmetry case, yeah. Okay. So I have a lot of time to talk about my last one. Okay, questions about this bouncy? Yes.
Does that more about the calculation this coordinator is doing? Because if I understand right, it is planning the trajectory for the ball, and it's planning this penalty terms, right?
Yes, yes.
And what kind of how it is solving for this?
So that one turns into, you solve it using an interior point method, and I'm like 90% sure that does let you get to the true optimal. And then I didn't show the math because it's kind of annoying looking, but we do have like all the details as well. So it comes out to be a problem that is, if you plot it, it looks convex, but the solver refuses to recognize it as convex, but you can just deal with it with an interior point method. Yeah.
One thing I didn't quite understand is like at the point where you actually compute the optimal trajectory, what task is left to be done for the pedal controller? Like you're still doing model predictive control for the pedal, right? But at that point, you already must know where to hit it and at what angle, because the global controller computes a trajectory, no?
So the global controller, sorry, so can you just repeat the first sentence of your question?
I forgot the first.
I forgot it too, which is why I asked. But so you're saying at the point of collision, are you asking what's left to do for?
Yeah, what does the pedal controller actually have to do?
So actually, so if this is the paddle, you only need to be actually doing work when the ball is approaching you, and once it's going the other way, you don't need to do anything.
Yeah, I was just wondering, like, if the global controller computes like the optimal trajectory, and then the pedal controller is just trying to match that already computed trajectory, like, do you?
So during that time, once it's going away from you, now the global controller works for every collision, right? So once it collides here, the global controller says, okay, left hand, here's your trajectory. It's not going to send like the right hand has no desired trajectory at that point. So you just don't do anything. I mean, it would be a waste of effort anyway. Yeah.
Okay, so you're saying the global coordinator basically plans the motion for the other hand?
Yeah, for the hand that the ball is about to reach.
Yeah. It plans that. It says, look, you have to be here now, or you have to be moving at this speed.
It gives you the entire trajectory. So like the ball hits here, immediately the global trajectory guy says, for the other hand, here is your entire course of optimal trajectory, like during this thing.
Okay.
Yeah,
so
during the ball's approach. Yeah.
it plans a whole vector of
Yes.
positions and times.
Positions, well, it's discrete time, so you don't need the times.
Positions.
Positions and cues and attention quantities. Positions and how important it is that you get to that position. Yeah.
Okay. And then the local thing, the local hand.
The local hand track just tracks.
We don't need MPC then.
Sorry?
Why do you need, why it's not a PID controller?
No, because because if you want to put the time varying queue penalties in, the easiest way is to do MPC. There's probably a weird way to do it with LQR as well. We just didn't really try it. Like to solve it like this optimally, you would need to do an optimization. I don't think it necessarily needs to be MPC in this case, but.
But did you use some standard package solver here, like that solves these quadratic problems?
Yeah, the bottom one is a standard package solver. The top one is a bespoke student-made solver. Yeah. Okay, cool. Okay. So that's 2/3 of the talks. And now we have the final third, which has nothing to do with layered control. Okay. So this one. So this is the vague motivation behind it. So all the other things that I've said so far are kind of in this column. So we have some behavior in neuroscience or in animals more generally, right? You're balancing, you're throwing balls, you're walking as a fly, right? And then you make a controller that models that, you do some simulations, and then you try to say something about the overall animal. This last third of the talk, I wanted to look at the right-hand column, which is the implementation. So for the animal, that would mean like what's going on in the nervous system, right? What's the nervous or neural circuit that causes the observed movement? And that roughly translates to like how the information flowchart is in the controller.
What's that thing in the top left? I just can't make out what it
This is a monkey with a ball.
From the top.
Where's the button? Yeah, this is not see it.
Wait, I'm very confused. Sorry. This is not the important image in this image. Just imagine an animal doing a thing. Okay. Okay. Right. Okay. So what I'm going to show you is basically a toy example because it took me a long time to think through the concepts. All right. So here is our toy example. Our plant is just a muscle fiber. Muscle fiber, okay, like Golgi tendon organ, this is not important. The muscle has a sensor on it. It tells you what force loading it's under. And then with some sensory delay, this the force information gets sent to your nervous system. And then your nervous system does some computations, and then it decides, here is what I want the muscle to do. And it tells the muscle to do that by sending a motor neuron with some firing rate, right? So you fire more, the muscle contracts, you fire less, the muscle relaxes. And in both directions, there is some amount of delay. This is a toy example, so we're just gonna say 10. This is definitely way at the lower end. Even for the Drosophila, there's 10. Okay. Okay, so the muscle model, you can write some simple like ODE standard model where F is the force and R is the firing rate of the incoming motor neuron. Okay. So what we wanted to do here, or what I wanted to do, was wanted to model the nervous system as a controller and then look at the circuit. So we've kind of done wishy-washy versions of this where we said, oh, the controller has this feature. So the feature is also going to show up in the nervous system. But this time I wanted to say, here is the circuit, right? It's probably not a very good hypothesis, but I just wanted to get to that like final concrete state. Okay, so we wanted to generate hypothesis circuits for a delayed controller. And then wanted to answer this kind of broader question. If I know what the input-output behavior is, what can I say about the circuit, if anything? Okay. Okay, so there's 3 steps to doing this. First, this is not the only way, but this is the way that I found. First, you build a controller that has the correct amount of delays in total. Then you're gonna force the delays to be in the right place of the controller by splitting transfer functions. You'll see what I mean in a moment. And then finally, we do the fun bit, which is we convert that stuff to circuits. Okay. So first we build a controller with the correct net delay. So here's that model again, right? Muscle delay, nervous system delay. And then for simplicity, we're just going to say that the total delay is 2, okay? 1 incoming and 1 outgoing. So we linearize and discretize our model of the muscle. And then you can write your controller in this way. So your final actuation is going to depend on your muscle state from the beginning of time, if you want, up to current time minus delay. Right? Because of these net delays, there's no way for that quantity to depend on up-to-date values of this quantity. Okay, and then in this case, we're just going to restrict K to be linear. It's optimal for linear systems anyways. Okay, So here I have skipped many steps. I've skipped a whole paper's worth of steps here, but this was a previous paper. So happy to talk about it more offline. Basically, how you deal with this is you just add a bunch of fake variables to your system, do some massaging, and then throw it into like MATLAB or Python DLQR solver. And it's going to give you a system, an optimal controller for your system with delays. And I've just drawn up the block diagram version of that controller. Again, I have more details if you would like to know. So the main thing to notice here is that, yes, we have 2 time steps of delay. That is the goal. We're just trying to get to the net delay. But the delays aren't really right in the right locations, as in like this delay is in the inside on the input and the output end, right? These 2 delays are right in the middle. So we wanted to more systematically generate stuff that looks like the thing on the right. So first step, very short. Okay, so to do that, we took this state space controller and we just put it back into transfer function. Transfer function doesn't care about implementation at all, right? It just tells you the input output behavior. Now, if there are any controls people in the room, when you have a transfer function, you're tempted to go back immediately to state space by applying realization theory. You cannot do that because you're going to start facing the same problem of like the delays will be somewhere, but they won't be where you want them to be necessarily. So to guarantee that the delays are where you want them to be, you do this simple thing. You just split the controller into 3 parts. Now you're going to force them to have the relative delays. So the simplest thing you can do is to make G1 and G3 into these. This is just a generic first order system. This has 1 unit of delay kind of encoded in it. I'll draw the picture later. And C and epsilon, you can choose them to be whatever. You can't pick C to be 0, but otherwise you're free to choose. Okay. Now, if you choose these 2 to be like that, then you're left with G2 to be equal to this second order thing, so that everything multiplied together gives you the original controller. Now, the K0, K1, and K2, those were given to you by the LQR program, by the like optimal control program. You can't change them, like you have to keep them there, so you keep having the optimal behavior. These are just like things you can do inside of the controller. Okay, so you split this, and then, so G1, that 1 unit of delay is going to be the 1 unit of sensory delay, and then G3, the 1 unit is going to be the 1 unit of actuation delay. And then, so you can draw, so like we usually draw control diagrams like this, but I didn't really like it. So here's a very first cut attempt. So I changed it from a diagram into a neuron, because I don't want to show this to like an experimentalist and say, where in your system can you see this, right? You don't look for multiplication blocks and addition blocks necessarily in the nervous system. 1 neuron can do all of that together. So here's the attempt at kind of making that conversion, right? We have these, in this case, 2 synaptic inputs. They get multiplied by some synaptic weight. Should be very familiar to everyone who's doing learning. Then you have the pink thingy is the neuron body. So the neuron body has some self-dynamics. So the state of the neuron can depend on the past state of the neuron. That's fine. And then you output it to the axon, and you can have the delays. I've drawn them in this way, but you can have them in a slightly different arrangement as well. It's basically a recurrent neural unit with no nonlinearity. Okay. And then you can convert your block diagram into a more circuit-looking thing. So that's this diagram, right? 2 inputs, 1 axon output, 1 delay unit. Okay, so we're going to go back to our block diagram and just redraw it as a circuit. So, okay, so for the sense, so for the 2, so remember we have these 2 like simple blocks that represent the delays. If you draw them using that method that I showed, voila, it's 1 neuron with the delay. Okay, we're good. Now, we have that complicated equation for G2 still. So now we're just looking for circuits of G2, and once we have that, we just plug that into this diagram, and then that's our hypothesis circuit. And everything matches. We have delayed sensing and delayed actuation. Okay. Delays are compatible, meaning they're in the right places. Now we have to find circuits for G2. As a reminder, should have put it there, G2 is this thing. Okay. Most of these are constants, so this is not a very bad transfer function. Okay. Last and most fun step, use controller realization theory. So a controller, sometimes it's just a static gain, but most of the time it's also a dynamical system. So you can write the controller also as a dynamical system. So it has some internal state eta, and then it outputs your U. if you're familiar with the other parts of control, this is like the ax plus b equation, just with different letters, okay? So you can take the transfer function and put it into different realizations. And then for the realization, because one neuron is only doing one scalar computation, you split into scalars. Okay, very boring. So then you split into scalars and you draw it as this giant block diagram. And then you convert it into the neural circuit. So here's neural circuit candidate number 1. I thought I saw a hand, but now I'm not sure. Okay. Okay, now here's the kind of fun or unfun bit, depending on your philosophy. Realizations are not unique. They're related by similarity transforms. If I have one realization, that is, if I have one instantiation of F, H, M, and N matrices, I apply a similarity transformation to get infinite amounts of F, H, M's, and N's. So let's say we say, okay, I want to do a simulation. I need actual numbers. I found a set of actual numbers that realizes my controller, and I poke the muscle, and then I do a simulation. So that's what these lines are. So we just did a pulse disturbance on the muscle, and we just try to reject that disturbance. We're trying to restore it to a set point. So I fix my numerical values, I simulate it, and let's say I get this blue line. Okay, that represents one instantiation of the values. That one says, okay, you're gonna have this circuit, and then the top neuron is gonna increase in its firing rate. The middle neuron is gonna decrease in its firing rate, and the output is gonna also decrease. The blue lines hidden on the purple. Okay. That's like a solid prediction. We can go try this out. Except now you apply a similarity transform, you get a different but equivalent realization. I do another simulation. Now it does the red line. That prediction says, if I poke the muscle the exact same way and you see the exact same behavior, the top neuron has decreased in firing rate, opposite prediction. The middle neuron has done this weird like decrease and then increase. And the output has also done this weird spike and decrease and increase. So you can play around with the parameters and kind of almost get whatever neural predictions that you want, okay? This is bad in the sense that if you have one behavior, you can predict many different things, but it's good in the sense that, well, it's unlikely that you know exactly what's going on in the circuit just from looking at the input-output, so it's nice to have this space of hypotheses that you can then kind of fit to what you actually find in the animal. Okay. Again, for those who know control theory, there are other realizations. So these realizations, this one is called the controllable canonical realization. Basically, it just puts zeros in specific places. If you have zeros, that's actually going to change the shape of your block diagram, which in case changes your circuit. In this case, I'm not really sure why, but this one actually turns out to be 2 neurons instead of 3. Fine, and then we can do the same trick as before, right? We have different parameters. In this case, we're changing the C and epsilon parameters, and you can change those parameters to give different neural behaviors. Okay, just for completeness, I have one more, which is the observable canonical realization. It puts zeros in different places. Whoa, okay, I don't know what happened there, but that's the resulting circuit. Okay, so I'm basically done. What else did I want to say? So these are the 3 circuits, summary figure. Okay. The other thing I wanted to say about this is, so if I have the one fixed behavior, I can take any of these, adjust the weights accordingly, and then use that to implement the behavior. If I just let the synaptic weights do whatever they want, each of these can just be generic second order dynamics. Okay, so if you change the weights, it can do a different control behavior. So any second order dynamics you can do with these circuits. So second order dynamics doesn't have to be second order control. It can also be estimation for a second order system. Possibly vaguely related to the idea of canonical microcircuits. So you see the same circuit pattern in the brain like over many places. So I guess you could think if we're doing second order computations everywhere, we'll just have the same motif over and over again with different ways to do the specific task. Okay. Thought I had takeaways, but I don't. So that's the end of the talk. Thank you.
So let's start.
I have to look in.
So the next speaker is Anand Subramoney. He's an assistant professor at the University of London. He's going to talk a very interesting topic about the scaling up deep learning in the future. Thank you. Right. So just as a disclaimer, there are different parts of my talk that would be like extremely obvious to different groups of people. So, and I've kind of made the talk deliberately a little bit provocative. So don't get too stressed if you think what I'm saying is like sounds very crazy or very obvious. Okay, and as Toby pointed out, you've seen this plot like lots and lots of times over the last few weeks. But so what I want to point out in this plot is the different paradigms of scaling that we have seen over the last few decades, right? So the first part was all the Moore's law scaling, which came completely from the hardware. And then the second part, thank you. And the second part over here was GPUs, as we know. So as we started hitting the Moore's law scaling limits, more parallel compute became the way to scale machine learning models. And then there is like this interesting third group of, or a third plot line over here with a slightly different slope. And this is where transformers started, right? So we had like algorithms that could scale slightly better on GPUs than existing MLP algorithms. So the question is, oh, this clicks
in the space.
Right. The question is what comes after that? So that's kind of like what I'm going to attempt to talk about. And so in my talk, there are like two parts essentially. So the first part for the first 20 minutes or so is like a bit of a perspective on what could come afterwards and how this is relevant to us as a neuromorphic community. And then the second part is I'll talk about some of the research that we are doing in my group and with collaborators that are kind of scratching the surface of these problems. And the title of the talk comes from this very nice paper from Liserson et al. One of the authors of, I believe, the Dragon book, the compiler book, if you've ever read it. And so this was written in 2020, right? And the point that they make is that software can be more efficient by performance engineering. So, I mean, so the room, if you don't already know, so the entire concept of room at the bottom came from a Feynman's lecture back in the, I think, late 50s, where he talked about how you can just improve the physics of hardware. I mean, so what he said implied that you could improve the physics of hardware to scale up computing. And that did hold true for quite a long time, and that was the Moore's law regime. But so as we start hitting the physical limits of what we can do with transistors, so the point that these authors make is that there is still room at the top. So scaling does not just have to be based on hardware. And there are a couple of things that can be used for scaling. One is software can be made more efficient by performance engineering. So restructuring. So this is kind of, yeah. So this is kind of obvious, right? So better implementations that take advantage of parallel processors and vector units. And this is kind of what happened with AlexNet and deep networks with GPUs. And then algorithms. So I'm kind of like making, and they also make this distinction between software and algorithms in the sense of implementations of existing algorithms and new ways of doing things. And algorithms can also offer more efficient ways to solve problems. And since the 70s, for example, the time to solve the max flow problem has increased nearly as much as from algorithmic advances as from hardware speedups. So this is a very important point, which is the specific way that problems are solved can make a huge difference in how scalable they are. And then obviously hardware architectures can be streamlined and also more customized. So apart from just like improving the substrate itself, there can be better architectures, and I guess like people over here already know that very well. So there are like three different ways of like scaling up. And what I'm going to focus on is mostly like the algorithms and a bit of software. And I kind of contend that this is where we should be focusing to scale up deep learning next. Because even with GPUs, we are starting to hit the limit of what GPUs can do and how well they can be scaled. And then there is this entire energy argument that all of you are familiar with very well. So I contend that we need to like really start thinking about different types of algorithms in combination with software and more customized hardware architectures to scale up deep learning better. And so a little bit of a kind of an anecdote. So if you're old enough, you probably remember Google and how cool a company it was. So Google was essentially starting to become popular when I was in my undergraduate, and it was really one of the most innovative companies that ever came out, right? So they used to do everything in an innovative way. So even the way they did their initial public offering was like quite different from every other company around in the Silicon Valley. And so there is, people have like kind of written about how Google scaled up. And so obviously, I mean, you probably heard of PageRank, hopefully, which was like their big deal when they started off. But one of the main reasons they succeeded was how they scaled up the hardware. So at that time, a lot of the scaling up was just like buying bigger and bigger computers. It's kind of similar to what we do today, buying bigger and bigger GPUs. So back then it was what was called vertical integration. So you would buy like huge servers with like insane amount of processors and hard disks and whatnot, and then try to process things faster. And with PageRank, they had to like index the entire internet. And so I looked it up yesterday. So that was about like 100 GB, which was quite huge back in early 2000s, right? So essentially what Google did was at some point they realized, oh, maybe they should just buy like cheap hardware. And so they went around, so that's kind of like a quote from this book called The Google Story. So a quote from this book called The Google Story, which talks about like how they scale up. But essentially what they did was they realized, oh, let's just buy cheap hardware because hardware is cheap. So they just sent like a bunch of employees to all the stores around to buy up like all the hard disks that they could find. The problem with cheap hardware was it failed a lot. So they built like an entire layer of software to handle these failures. And then they basically were able to do scaling, well, I mean, almost get like infinite scaling because all they had to do was buy more and more cheap disks. They already had the software to handle this. They had replication. They had everything that was necessary to kind of handle this cheap hardware. And this made their costs really, really low. And they were able to scale up to what later became known as Google Scale, right? And which I think still stays today, although it doesn't get as much publicity. But Google essentially has like their own hardware infrastructure, their own networks. So they have like basically their own internet, as it were. And they really run things at very large scale. And then later, so based on this idea, there were like things like EC2, distributed databases, because what do you do if you want to store petabytes of data? You can't just buy like a petabyte hard disk. I mean, you probably can today, but it probably costs quite a lot, right? And so companies like Amazon, they started doing distributed databases. So you buy like a lot of cheap hardware again, and then you start replicating the data, run cool algorithms like Paxos on top of it to make sure that you don't lose data, and then you can store like infinite data, right? So you just buy enough servers to store as much data as you want. And this approach has been extremely successful in this regime of databases and general purpose computing. But machine learning hasn't really seen this kind of scaling up yet. And so this is kind of what is, I mean, one way to think about it is distributed model parallelism. So this is both for training and inference, but this is really like a way to achieve almost infinite scaling, because no matter how amazing hardware you have, whether it's GPUs or neuromorphic chips or whatever, you can use this method to scale it up further, right? And I argue that in the neuromorphic community, we are like uniquely positioned to like understand this kind of scaling. We already worked with a lot of these primitives like sparsity, asynchrony. So a lot of the things that we think of as like biologically inspired ideas, well, I mean, they're kind of come down to the necessity of, I mean, almost like a physical necessity of scaling beyond a certain point. And so, so when I kind of got into machine learning, which was before 2010, as it was, so the kind of what I thought about, or at least naively, my idea of like scaling up neural networks was this: to do parallel and distributed computing. So I hadn't like read the PDP volumes yet, but I mean, this kind of idea like made a lot of sense, because you really have this architecture which is distributed and which can be run in parallel. And so what I thought of was, you have an artificial neural network where all the units run in parallel, each one asynchronously receiving input, updating its own state based on this input, and communicating with other units when necessary. And it should also be robust to delays and failures of communication and failures of units, right? And so training also needs to happen in this same setting continuously. And if this sounds a lot like what the brain does, I don't think is completely accidental. And so afterwards, when I kind of started learning more about neural networks, I realized that I guess a lot of the mathematical formulations, so there are like a lot of places where it's not obvious how we would do this kind of model parallelism, especially with asynchrony, and certainly sparsity was not a big thing back in those days. And so that's kind of, I think, one way to kind of approach this problem of scaling, which is to use model parallelism. And why do we want to do this? So I already talked a lot about this, but especially with distributed systems, one of the most interesting features is the robustness to failures, right? So you want to have large networks running on like lots and lots of nodes, and nodes are inevitably going to fail. So even if your probability of failure is really, really low, if you have enough nodes, then you're going to get like failures almost every hour or every day. And the other cool thing about this way of scaling is that if you develop reusable primitives that can be mapped onto any hardware, then this can work on heterogeneous systems. You can use the appropriate system for different parts of your overall model and still scale it up. And so these same algorithms can lead to energy efficiency as well on small neuromorphic hardware. And this also kind of allows you to use existing hardware effectively, even analog ones. And as I said, there's a lot of intersection with biology in terms of how this scaling works. And essentially, this kind of like top-down approach to think about what algorithms we need that is independent of the mainstream research, independent of like prior beliefs for using and scaling up models on different hardware paradigms is kind of what I'm trying to do, and I think more of us should be trying to do as well. And there are also like all of these kind of very obvious arguments about environmental sustainability that you're all aware of, access to AI, because I mean, right now you still need a lot of GPUs to run the large models, right? It's not like it's accessible to everyone. And I was kind of thinking about how long is it going to take for us to be able to run these kind of models on a phone? And at least with the current technology, it doesn't seem very obvious that this is going to happen anytime soon, right? If you have like a 400 billion parameter model, we're not really making too many advances in hardware. We are already at like limits. So if it is based on parallelization, then you need like more space, more energy. So we are not like even close to running things on a phone, like really capable models. So probably, I mean, I'm happy to hear if you disagree. I'm definitely no expert in hardware, but that's kind of like the sort of thing that we need to be able to have everyone access AI, assuming that's a good thing, of course. And then obviously interaction with the real world, edge AI in real time. So all of this requires low power, it needs like fast responses. So all of these scalability primitives are not just about running models at like a large scale. It's just like running models using a different paradigm that's potentially more efficient and potentially like kind of better at running on like a large variety of systems. And a big part of this is learning, what is called on-chip learning, right? Because if you're not like learning on the hardware, then it's really hard to try out new architectures. So let's say you come up with like a really cool alternative to transformers. They're probably going to run, they're probably not going to scale on GPUs, right? So how are you going to try out and even test whether your cool new architecture is going to scale up as well as transformers? So that's kind of like a big part of developing like a hardware, which is you need to be able to train on the hardware as well. Otherwise, you would never be able to say whether this is as good as transformers or better or whatever, because there's just like no way to test this. And on-chip learning also has other advantages in terms of adaptive, flexible, private edge systems, and also like training existing large AI models at better energy performance point, because that's obviously also kind of like reaching a sort of ceiling in terms of how much energy these models are consuming. So I kind of like wrote down some data for distributed model and training parallelism. So there are some of these things which we have already, things like efficient communication between model units. Asynchronous training algorithms are things that do exist, but there are only like a few people working on this. One of them is, there is a group at Google trying to train models across data centers, right? So they have like these asynchronous training algorithms where they essentially distribute like large models across like different data centers across the world, and then partition the data between these data centers and then train them locally and communicate, and then you end up with like this larger model. Hardware-aware design of distributed ML models. So, I mean, a lot of the advances or a lot of the kind of progress that's been made in deep learning has been writing GPU-aware code for the models, right? So, acceleration kernels. So, just kind of like taking advantage of what the GPUs have to offer and using its memory hierarchy appropriately and so on. And for distributed ML models, we need this as well. And then correct inference algorithms for model units that communicate only asynchronously. So this is like an interesting area because at least as far as I'm aware, in the algorithmic space, there has been very little work done in this area. But obviously, people who design hardware, like we saw in some of the previous talks during Telluride, people who design hardware really think about completely asynchronous implementations of algorithms. And it just feels like those of us who design algorithms should also be thinking about this, because this can be done at the algorithm level as well as the hardware level. And then handling failures of different units and nodes. So this is something which, well, I mean, I have no idea how we would do this. I guess there is like some older research from computational neuroscience about how neural networks might be able to handle failures of different units and nodes, how it's robust. But actually building a system, and especially a large-scale system that is able to do this, well, I mean, I haven't seen like any recent work on this. So yeah, I mean, these are kind of, I mean, there could be like a lot more, right? But these are kind of like naively some basic things that we would need anyways to build distributed model and training parallelism. And so these bars over here, the report are just like my kind of impression of how much progress we have made in each of these things, right? And with efficient communication between model units, we kind of, I guess, know how to do this to some extent with like event-based communication, with sparsity, all of that. And then some of these things are just like very, very, very at a very nascent stage. And just to kind of like connect back to what I said about biology. So, I mean, we all know biology, I assume, in terms of like the biological principles that we try to use in neuromorphic computing. And so this is just like a list which kind of partly covers the features that we need for distributed model parallelism, right? So sparsity, event-based communication, asynchrony, temporal coding, which is probably like a little bit more specific to biology, and then locality, right, in both time and space. And I mean, one of the things is, I mean, this is probably, so one of the things is obviously like with the biological spiking networks, these were developed as models of biological neurons, but then they're kind of like, at some point, people were trying to do, or people try to do neuromorphic computing with this, but then these are not really models that work very well for deep learning, right? So these are like models of biology, they kind of work for some tasks, but then they don't always like scale very well. They're probably like very suboptimal for doing any sort of deep learning. So from the other direction as well, we try to like think about designing deep learning architectures ab initio for deep learning on neuromorphic devices. And by distilling this essential advantageous properties of the biological models, but really being more goal-oriented in terms of doing deep learning or doing machine learning and solving those problems directly. Okay, so that's kind of like my perspective part of the talk. So if there are any questions or any comments, I'm happy to take them now. Yeah.
in the desiderata part,
Mhm.
you did not mention online learning.
Online learning. Oh, that's kind of okay. I mean, that's kind of like a combination of these two, right? But yeah, so online learning would be part of it. I mean, so yeah. I mean, I guess like when you're kind of usually when you think about deep learning, you don't think of learning and inference like completely separately, right? So you kind of assume that you would be able to train the model on the hardware that you do inference on as well, for the most part. So, but yeah, I mean, it's definitely like not necessarily the case always. Yeah.
Why do you think it's the case that you should be able to do both training and inference on the same chip?
Oh yeah, so that's what I
There's
said.
really different kind of like computational kind of primitives and kind of like also in terms of like data, kind of ratio between compute and data is like the arithmetic intensity is really different, right? Learning it.
Oh yeah. So I mean, I guess my point was that you need if you design new architectures that are not appropriate for like current hardware, then you need to be able to train them on like different hardware to scale them up.
Mhm.
So which means that I mean, I kind of like assume that this is going to be like the same chip, but I mean, you're right, it doesn't have to be. But you could really have like completely different modes for like training and inference, right? But the point being that you need to be able to like train new architectures which may not be a good fit for existing chips.
Can I continue on that point?
Yeah.
So in fact, even us, I mean, we have online learning, but probably if you think of us as a machine that was trained from small cells to now,
Mhm.
that training process was not the same as what we're
Mhm.
using now to say understand your talk. And so there has to be two different machines, right, or multiple machines to train our models, and basically to train inductive biases. And so I would agree with the idea of we need online learning, but only for this much, and there was this much before.
Yeah, sure. Yeah, I mean, I wouldn't agree that we need to have that, but we probably.
But we do already.
Yeah, we do. I can.
train
Yeah.
LLMs, and then we fine tune, right? So or even if you see the attention or the SSMs doing in context learning, that's also learning, which you train to do learning. So there's, in fact, we are already doing it.
Yeah.
We are learning.
No, yeah, I mean, my point was like a bit broader. So I was not like trying to say, oh, like we should always be able to train on the hardware that we run it on, but that we need like this space to try out new architectures. So we need like new hardware to actually like scale up different architectures that may not work on GPUs, for example. Right? So that was kind of my point. So if you're kind of like designing something for GPUs, then you're already kind of constrained by what GPUs can and cannot do.
I kind of agree that, well, maybe we should discuss it. The time.
Yes.
So another thing very difficult to sort of discuss maybe there's different points if you don't have examples, because sometimes it's the granularity is sometimes beyond levels, sometimes it's the model, but also the size of the model effect. What you say about this point. So do you have an example of some?
Yeah, so I will be talking about, well, at least for some of these, we have done like some work on this. So I'll be talking about that.
Okay.
Yeah.
Let's get to that.
Yeah, okay, yeah, I can get to that. Okay, so so one of the early works that we did, so this was already like a few years ago, was to look at this first combination of like sparsity and event-based communication. And so this was, should say this was done at a time when state space models weren't very mature yet, but it kind of like, I think, demonstrates some of these principles. So what we wanted to do was first like tackle this part of doing, well, I mean, like more challenging tasks in deep learning with kind of event-based architectures. And so we kind of thought, like, so we have like the leaky integrate and fire neurons or adaptive neurons or resonate and fire neurons or whatever. But there are also like, there was also like a lot of work in deep learning about what sort of dynamics of recurrent networks would work well in practice for machine learning, right? So we thought, why not take one of them and just add this kind of gating function or event-based mechanism for one of these networks and see if it works well for like the tasks that those models are known to work well for. Because by 2018, for example, people already had like a billion parameter LSTM, as it turned out, right? I mean, it just didn't work as well as transformers, but it worked like reasonably well. And so what we did was we took the dynamics of the gated recurrent unit, the GRU, and put a thresholding function to make it event-based. And so in this kind of mechanism, what happens is that the activity, so you kind of get activity sparsity quite intrinsically in this model, right? So you kind of have the state dynamics, and the state dynamics are kind of determined by the gated recurrent unit. And there's a thresholding function which kind of decides whether to send messages to adjoining units or not, to connected units or not. And so this is just like a spiking network, but with like different dynamics. And what is interesting about this, and this is true for spiking networks as well, is that if you train this with surrogate gradient backpropagation through time, so in principle, at least like the backward pass is also sparse, right? Of course, like GPUs cannot take advantage of either of these sparsities because it's like dynamic sparsity, it's unstructured. But if you did have like the right hardware to run these models, then you would be doing a lot less computation, both in the forward pass and in the backward pass with backpropagation through time. So with these models, as it turns out, I mean, we kind of tested these models on lots of different tasks. And even with language modeling, these models were able to kind of do as well as like the best recurrent models from like 2019 or so. So which was this LSTM based model, but much more efficiently. So just to kind of like look at this a little bit more closely. So in Wikitext 2, for example, the effective multiply accumulate operation was like 17 million compared to like 32 million for the LSTM models, with this almost the same level of perplexity, right? So we kind of, with a slightly larger model, we get like much closer perplexity with very high levels of activity sparsity and backward sparsity as well. And so this is, and then, so this model kind of like intrinsically has this trade-off between the sparsity in the backward pass and the perplexity that you can reach on language modeling. Because in the surrogate gradient, you have this surrogate function, and you can kind of change the width of this function to control how much backward sparsity you want. And so yeah, so you have like this nice trade-off, which has like a point that you can choose, which has like the best perplexity for the constraints that you have.
Can you go back and you don't understand the plot? What are the axes?
The x-axis is the width of the surrogate gradient. And in the y-axis, it's like a double axis with backward sparsity in percentage and the perplexity of the model.
But which is the red? I can't see which is red here.
So the red is the backward sparsity.
So as you increase the width of your surrogate gradient, the sparsity goes way down. Is that right?
Yes, exactly.
And as you increase the width,
The perplexity goes down
which is
up to a certain point,
which is good or bad?
which is good. So the lower the perplexity, the better. Right, and then it kind of like tapers off. But so you
get about half the max in this thing. You reduce the max by about half, or maybe 2/3 in this. In these big RNNs, right? These are really big RNNs. I don't know how big they are.
Yeah, so this is like close to, yeah, it's like 70 million parameters or so. I mean, so the point is you want like as high sparsity as possible, right? So you want to be, you want to be as much on the left side as possible. But then if you don't want to like compromise on perplexity, you still have to choose a point where you only get like 30% backward sparsity.
You saw Shichi's talk the other day, right?
Mm-hmm.
And that's the delta RNN, from Galileo.
Mm-hmm.
It basically also a sparse RNN that uses temporal sparsity.
Yeah.
Like if the activity doesn't change by more than a certain magnitude, you don't propagate. What's the difference I never got it straight. What's the difference in the EGRU?
Oh,
Is it temporal sparsity or literally just activation like null hop?
so this one, I mean, so I think the conceptually they're like very similar, right? But in practice, so this kind of uses it's like the simpler mechanism of just like the thresholding function, like a spiking neuron.
Thresholding on what? Because the delta network threshold the change in activation between time steps.
So this thresholds the state. So it's just like a spiking neuron, right? So if the state goes beyond the threshold, then it fires, but if not, it doesn't.
But how does that work when you, what activation function does this GRU use? Is it sigmoid or tanh? Sigmoid, right? It has to be sigmoid because then therefore.
No, it's a bit more complicated than that. So let me actually see if I have a slide, but I mean, essentially.
Let's discuss it later.
Yeah, but you have like a linear combination.
Yeah.
So you basically get like, you have like a proposed state, which uses like sigmoid and sigmoid gates. And then you kind of have a linear combination where the state, so there are like two gates. So one decides how much of the new state to take in. And the second state is kind of how much of the old state you want to forget. Right, so it's kind of like an LSTM, but with two of the gates kind of joined together, as it were. And so that's the state, and it's like a very nonlinear function in the inputs, but it kind of you can still threshold it, and you can kind of still use the thresholding to decide when to send an event or not.
So it's like the null hop sparsity. Basically, just whether it's active or not, you propagate it.
Yeah, pretty much.
Okay.
Yeah, but Toby, he's talking about the sparsity of the gradients. In the slide you were asking that question, he was talking about the sparsity of the gradients. I don't think that's what.
Oh yeah, so I mean, so it has like a sparsity on both directions. Yeah, so that's for both training and activations. Yeah.
It's a quick question to exactly that point. The sparsity of the gradients. I mean, I get it that you have to perform fewer max, but now you need to keep track of what events you had when, and you need to store all of this and so on. And I think you're basically translating from a dense matrix where you access every element, you have a lot of max, to a sparse matrix where you have more complicated indexing, and then for the few values where you do need to index, you have float operations. But I'm just never sure when people make these comparisons about sparse and dense if it's really true that it's so much cheaper.
So, but why would you have more? Why would it be worse than normal? Because you still, I mean, in the normal case, you store like all the activations at all the time steps, right? And in this case, you store some of the activations at.
Yeah, it's indices, which of the right, like if you store a sparse matrix, you need to. It's a different format how you would store that, and then addressing that is more complicated, and you can't parallelize it so nicely and so on, right?
No, but that depends on the structure of the sparsity, right? I mean, that's kind of like a very general thing with sparsity, and this definitely you won't get any advantage on a GPU. That's for sure, right? Because this is like unstructured stuff.
But then also, if you want to do gradient descent, you need to store, right, like the history of like which thing was active when, in order to know where. No,
That's a very.
Just one bit extra to say whether it was active or not.
Yeah. I mean, you're not going to do worse than normal.
Okay.
No, but you need to store the intermediate states. That's right.
Yeah.
But to give you one example, so we did this on the graph core, and it was 20x speed up over GPU. So that is really
Which level of sparsity?
Huh?
At which level of sparsity?
It's like 7% active, so it's pretty sparse.
7% not okay, but this is 30%.
Yeah,
Yeah.
that's 70% active. Right.
This is
Yeah.
70%.
Well, I think this would be a great thing to discuss through in the NIC topic area to get this straight, because you guys never talk about delta RNN when you talk about GRU, and we never talk about EGRU when we talk about delta RNN. It'd be good to actually get it straight.
Oh yeah.
What's the pros and cons? And also, you guys know that we did this work on sparsifying BPTT, and we showed that you have exactly the same sparsity in both directions. In fact, the beautiful work of T. Chan, our student, showed that when you're doing PPTT, that the memory requirement is actually very small. You don't need to store the matrices at every time step. You just need to store the activations at every time step. So it's a tiny bit of memory compared to the matrices.
Oh, you mean like with the event prop or?
No, the paper is not well known, but it's quite a cool paper.
No, you just keep track of the neurons that were active when you do the forward.
Oh, yes. At each time step, you only need to know the neurons that are active, not the weight matrices.
Mm-hmm.
Not the gradients at every pair of at every connection.
Oh yeah, sure.
Yeah, so it's quite cool actually.
Yeah.
But it's not,
But I think like just for the delta RNN thing, so I mean we were like aware of delta RNN, but so our main goal was to do language modeling.
Yeah.
And in machine learning, language modeling, at least with recurrent networks, seems to work well only with like LSTMs and a bit less with GRUs. And so this was kind of our target, right? And with delta RNNs, I mean, we didn't really like directly compare it, but I don't know if you ever tried language modeling with delta RNNs.
Well, actually, we did. It's probably some archive papers in somewhere.
Okay, I see.
I
Yeah.
look
I mean,
at
we use stuff
they
like
need to
doing-
try with the wiki types.
Mhm.
He didn't get the same, as I remember, he didn't get the same benefit as much as before.
Yeah, exactly. I mean, even with GRUs, you kind of like already see, I mean, here, I mean, this is like an LSTM model, and this is just with a normal GRU, the perplexity already kind of goes up. So language modeling is very, very sensitive to the architecture of the network.
What's the width effect here?
The width,
Yeah.
so each layer is like this number. So there are 2,000 neurons, and with about like 3 layers.
The width of the circuit function, we say that it gets wider, then it gets sparser. No, which way does it go?
Oh, yeah. Oh, the surrogate gradient. Yeah. So as it gets wider, it gets less sparse.
That's the ones.
Yeah.
Get better. So it's,
Yeah, but less sparse in the backwards.
yeah.
Yeah. And so, I mean, I don't have a slide, but also because you mentioned just storing the events, so you can actually do event prop with this. So this is a formalism where you can derive event prop. We have this in the paper, and then you really only need to like store the events, and then you would have like exact gradients propagating through it. Right? And the thing with another nice thing with the GRU is that you can write it as an ODE like very nicely. So it's much like a def neuron. And so it makes it like a lot easier to do event prop. So LSTMs are a bit more tricky to write as an ODE, so that gets like more complicated. But there are like details in this paper. And we did implement this on Spinnaker 2. And so with in Spinnaker 2, we kind of had to like also prune the network, have parameter sparsity as well. And so we did a measurement with single batch inference, and you can kind of see that even with all of the generational differences and kind of all the limitations of Spinnaker 2, it's still like slightly more energy efficient than this GTX 1070 Titan, and much more than A100 for single batch inference, right? So and implementing this on like Spinnaker was like much easier compared to a lot of the other kind of like deep learning models, just because I mean it's a recurrent network, and then it kind of has a natural fit in terms of like how the sparsity is mapped to the hardware. Okay, so right, so as I said, so this is like event-based, sparse, low communication overhead, but it is not asynchronous, right? So there aren't really any completely asynchronous formulations of event-based models today, and we don't have one either. But just to kind of point this out, that it's only event-based, but there is still a shared time across all of the units in the network. Okay, so the second thing that I'll talk about is asynchronous event processing. And this is really asynchronous, at least like in the event processing part. Because I mean, we have all of these nice data sets from DVS cameras, from there is also like other data sets like climate data, epidemic case detection, where the data is not really on a fixed time grid, right? So it's not like that. It's not that you have like this kind of even distribution of the samples across time. And ideally, we would like to process this data as they come in, rather than having to wait for some time and create frames, or like do any sort of like aggregation of these events. And so for this particular use case, linear state space models are amazing, right? Because they kind of, well, I mean, they're linear, which means that you kind of can keep the state in between the units. So maybe it's kind of useful to look at this. So each of these gray squares, three-dimensional squares over here, is the time when the input is coming in. So you have the state of the state space model, and then whenever an event comes in, you update it. And then because it's linear, you don't really have to calculate the state in between, right? You kind of, the next time the event comes in, you can directly calculate what the state should have been of the state space model at that point, and then you update it based on the new event and so on. And if you plot this with like this on the real and imaginary axis, then this is kind of like what you see. So at every time an event comes in, there's like this jump in some direction, and then it kind of like decays, and then there's a jump again, and so on.
See anything. What do you do?
Oh, this pointer is not really working, is it?
No.
Oh, what happened to the pointer? Let me see. Yeah, can you see it now? It's still quite small, I think. I don't know if I can increase the size, Sandy. But I was just pointing at this this thing over here. Yeah. So this kind of flow.
Just to clarify, like even because it's linear, you can exactly compute the state of the system, or what
Exactly.
like the
Exactly. I can exactly compute the state of the system.
Okay, that makes sense.
Yeah. So you don't have to like simulate the network when you're not receiving events. That's the point. And this processes like events really as they come along, right? So you don't have to do any sort of computation when there are no events. And that combined with something called event pooling, where you kind of, so usually like with what we observed was with things like DVS cameras, so you have like lots of events and they're like very redundant. So we found like a huge benefit in just like downsampling the events across the layers of the network. And then it just becomes like just more tractable. And we did this with the S5 model. So I think I'll probably skip the details of the S5 model. You probably know this, but
I hope you don't expect us to read that.
I was hoping that you'd be able to read it, but this is quite small, the projection. But okay, so what you see is spiking speech commands. This is spiking speech commands. This is like the best accuracy for spiking Heidelberg digits, the best one. And for DVS 128, ours was like 97.7. So we actually have a new model which reaches like 100% on DVS gestures based on like the same thing, but instead of using an S5 model, we use a Mamba model, and then it reaches like 100% test accuracy with all of the gestures on DVS 128. And for both of these spiking speech commands and event SSM also, the newer model works like much better. But this is like a model that is like really processing the events directly. So there's like no frames, there's no aggregation whatsoever. It just like takes the raw events and processes it. Okay, and it parallelizes very well on GPUs because of state space models. So it trains really well, and there are no surrogate gradients or anything. So the model itself doesn't have like any sparsity, right? So this kind of only solves this one part of handling inputs asynchronously. Okay, so yeah, so that's what I just said. Okay.
So
Yeah.
I don't quite understand what the model actually does. Like, I think the picture that you showed, like, intuitively it makes sense, but that's like if you're tracking a single pixel or something. But like, what is the objective of the model? Like, you're trying to classify events.
Detect gestures, like
Yeah, sure.
rotating right, rotating left. So.
But how does the model here help you integrate like many different events? Like the picture, like, I don't know. Anyway, okay, and I will ask you afterwards.
So
Maybe explain the S5 so how.
yeah. I mean,
the S5 model obviously doesn't operate on individual events, right? You operate on full image frames, right? So even it's an individual events, yeah.
but but that's, you just have like that's just like an additional dimension, right? You would have, instead of, it's not going to work on like scalar input, so you'll have like vector input. But for each of those dimensions, you would still have this property.
So you plotted the image, then you have just multiple channels, right? In S5.
Right.
Same. So most of the channels will be like at 0, right? And then you will be some channels with some pixels are changing. So you have like a high activation spot, even like spot.
Right. And you're updating the internal state only when an event comes in. Okay. And then
exactly.
you this through multiple layers, and then the other layers, like each of the layers in the model generates event outputs. And
yeah, so it's kind of like there's a subsampling, but essentially yes. So whenever there is an event, then only at that point the layer produces an output that goes to the next layer.
I see.
And then if there's subsampling, then you kind of decide whether it does go to the next layer or not, or you kind of wait for some time before you go to the next layer.
I see. So the whole pipeline basically gets triggered whenever there is a spike coming in, and it propagates through, but maybe not all the way through. Okay. Yeah.
But how many ops per event do you need to do? How many ops per event?
how many ops per event.
Yeah.
Uh,
Run the whole space-based model for each event.
No, with the subsampling, you only run like some of the initial layers, but we didn't like very carefully look at how many ops per events. So we don't have that number.
Yeah, okay.
Yeah.
Do you have an understanding why it should get 100%? Like what
Well,
was
that's
the
that.
extra bit that was, you know what I mean? To get 100% almost feels like you'll memorize it.
No, but it's 100% of the test set. I mean, so I guess it's
Yeah, but still, even if it's 100% tested.
Right.
You know what's going on? Oh, it's a very easy task. Oh, I see. Okay. Not like it's levels and proof features.
yeah. I mean, that's kind of. I mean, it's yeah. I mean, that's true. I mean, it's more a reflection of the data set than the model. So I mean, I didn't say 100% to kind of say that the model is like amazing. So that's like obviously the data set is like too simple. That's what I mean. So yeah.
What's the exact number?
For what?
Is it 100.0?
Yeah. I mean,
So what is it?
no, it is 100%. It gets like all of the classes right in the test set.
It's the magic training run where that happened, I think, probably.
The what?
The magic training run where that happened. It happened to get, did it happen every single time you trained it?
Yeah. I mean, it's very robust.
Okay.
Yeah.
I mean, some of them have to be mislabeled, right? Like nobody gets 100% of this stuff. Don't get it.
I mean, this data set seems to be like much easier, but I mean, we found this to be like quite robust, and so it seems like maybe there's like maybe the test set is not from as different a distribution as it should be. So that's at least that's what it like looked like.
People are skeptical.
Yeah, yeah, but there's all the code is available. I mean, you can run it for yourself. It's all on GitHub. You can test it.
How fast the accuracy evolves as the events come in? No,
Yeah.
I mean, do you wait to the end, or if I just kind of watch how the accuracy evolves as events come in, do you see any differences?
Yeah, we didn't look at that, but that's a very interesting.
This is an important point because some people just try, say half a second, and then the actual sequences can be like 10 seconds.
Yeah.
If you try to classify it for 10 seconds, that's
Yeah,
much
just
easier.
too long.
Yeah, I mean, all of this was like really taking all of the inputs before putting the class
The
label.
entire sequence.
Entire
So it should be repeated many times.
Yeah. But we just like didn't look at the intermediate things. But I'm sure that at some point it would like get very close to this accuracy without having to process the entire one. But we just didn't look at it. Yep.
Okay, and now 10 minutes.
Oh yeah, okay. Okay, so since I have only 10 minutes, so let me quickly talk about this. So the third thing is asynchronous training. So this is something that we have been looking at. So we all know the locking problem, I hope, but essentially with backpropagation on feed-forward networks, you have this bottleneck where you have to first finish the forward pass, and then you do the backward pass, and then you do the forward pass. There's like a lot of time when your devices are not like really doing anything at all. So this is like basically a locking problem. And so what we did was we wanted to see if we could completely like ignore the locking problem. So in the sense of we make the updates as soon as it's available, and we make the updates layer-wise as well. So as soon as an update is available for a certain layer, we immediately update the parameters. And so in the forward, so there are essentially, I mean, this is kind of like an illustration where you have like one forward thread and two backward threads, because usually backward pass takes like about twice as much time as the forward pass. And the goal is to kind of have like full utilization of like all of the devices. So as soon as a forward thread is done, backward pass starts, and then as soon as one of the updates for one layer is available, that's immediately made to the parameters. So which means that forward passes often get like inconsistent view of parameters. So they might get for two of the layers, they might be using like parameters from previous update, and then for the third layer, they might be using a parameter from the current update. So it's essentially there's like no synchronization or locking at all. So updates just happen as soon as they come along. And so what is interesting is this actually works extremely well. So especially if you look at like wall clock time for training. So we mostly tested this on feed-forward networks, SNet 18 and 50 for CIFAR 100. And so in this table, this is like time to accuracy. So we have like a certain accuracy that we wanted to reach. And then we look at how much time it takes to reach the accuracy, and then the number of epochs that it takes to reach it. And our algorithm is called PDASGD because it's like partial decoupled asynchronous stochastic gradient descent. So asynchronous stochastic gradient descent is something that people have looked at quite a lot. And in general, there are like various variations of like how or where the synchronization barriers are removed. And in our case, we are kind of adding these couple more features, which is to do this layer-wise, and also have like a proportion of compute for the backward and forward pass that is like keeps the utilization maximum for all of the devices. And so what you see here is compared to like the more standard distributed data parallel training that is like very common with models. The asynchronous gradient descent essentially takes like less time than even that. Okay, so and a distributed data parallel is like I mean, if you don't already know this, the idea is that you just like distribute. You run like multiple copies of the model on multiple GPUs, and then use like different subsets of the data, and then you synchronize all of the gradients and all of the updates once all of the GPUs are done with their computation.
But does it reach the same asymptotic accuracy?
Yeah, so it gets like very close, like within 1%. And depending upon the task, it might be like higher or lower.
How about then doing it like 90% using the method for the last mile?
Yeah, so I mean, so this time to accuracy, what we did was we chose like the lower of the two accuracies and then saw which one reached that faster. So lower of two accuracies from synchronous and asynchronous training, and then see which one reaches that faster. We also, in the paper, we also have results on like time to the best accuracy as well. So you can look that up. And I mean, this is kind of like what the training curves look like. So the blue one is the asynchronous training, and the red one is the data parallel training. So the first column is the wall clock time, and the second column is the epochs. So essentially what you see is that the point here is that they both take about the same number of epochs. So they take about the same amount of data and computation to reach a certain level of accuracy. But the asynchronous training reaches there like much faster in terms of wall clock time, because it's just like consuming this data like a lot faster. And so this asynchronous training, we also measure the model flops utilization, so the hardware utilization, and this improves quite a lot on distributed data parallel. So you essentially go from 30, 28, 30% of utilization to about 50% utilization.
What does that mean? You model flops smoothly. Everybody else know what that means.
So it's kind of what percentage of the time you're actually doing compute on the GPU. So it's like how much you're utilizing the GPU essentially.
In percent, okay.
Yeah, in percent. So a model flops utilization. I mean, so that is so the normal flops utilization is you can just like directly look at how much compute you're doing on the GPU, right? But you can obviously like game this by just having like a super inefficient model, and then you have like 100% GPU computation all the time. So model flops utilization is kind of like narrowing it down where you compute like the maximum utilization based on like a canonical version of the model, so that you cannot like just make it like inefficient and then claim that you're doing 100% GPU, 100% utilization. And then you compare the utilization that you actually get with this canonical maximum. So that's what is model flops utilization. And the third interesting thing with this asynchronous training is that, so what we did was we kind of introduced delays in communication between different GPUs. So because in heterogeneous hardware, you often have like stragglers. There might be like one GPU which is just like really slow for some reason because somebody else decided to run some simulation on it at the same time or something, right? And with distributed data parallel, the more delays, communication delays you have, the slower the wall clock, the longer it takes to reach a point, because it has to like really wait for the synchronization. So if there's a delay of a certain amount, then it just has to wait for the amount before the synchronization is done.
How does that impact the accuracy? I mean, it's clear that it's not going to change much the time, but how about the accuracy?
Oh, the
accuracy be updated much less, right?
The accuracy like remains the same. We kind of like control it for the accuracy, so that doesn't like change that much. So and I mean, yeah, we introduced like delays in terms of.
Sorry, but how can that be? I mean, one just never updates, right? So we basically have one layer that's locked to the previous weights.
that doesn't.
Yeah, but this will still make progress because you have like, if you have like, at least if you have like multiple backward threads, multiple threads that do updates, then if you lose one, then you're probably going to take like slightly longer Moore's-law time, but it would still converge because it's not like any different from doing the asynchronous gradient assembly. So you can kind of like play with the number of backward threads and number of forward threads. And if you have like more than one for any of those, and if one completely fails, as long as there's like one remaining, it would always make progress.
So the idea is that not that you map the models like single model like multiple GPUs, but you have replicas like to distribute the data power basically in this context, but you make it asynchronous. No?
Oh, no, say that again.
So you don't shard like the model layers like of multiple GPUs.
Oh yeah. So the entire model fits on a GPU at the moment. Yeah.
Sorry?
The entire model fits on one GPU.
Okay.
Yeah.
And so how does the delay come in? Like how is it like basically like the layer level?
No, so the delay is between like the updates. So you kind of do the forward pass and then you do the backward pass, but the backward pass updates have to be communicated to the other GPUs, right?
Okay, so you do
And there
have
can be
multiple
delays in that.
GPUs.
Hmm?
So you do have multiple GPUs.
No, yeah, we do have multiple GPUs.
Okay, so it's distributed data parallel, but
yeah, exactly. I mean, that's kind of it's kind of like distributed data parallel, but without the sync.
okay. So
and the layer
it's not that you don't update the layer, right? So
Yeah,
it's that you receive the gradient from one of the replicas.
Exactly. Yeah.
That makes sense.
So as long as you have like one remaining thread, you will always make progress. Yeah. Okay, so I think how am I doing on time?
You're out of time.
Okay, I'm out of time. Okay, so I'll skip this, but this is like a more of an approximation for avoiding this locking problem on training. So you can look up the paper. So all of these are preprints. I have somewhere at the bottom, I have the first author, but you can, if you look on my profile, you'll be able to see this. So this is like a variational approximation for avoiding this locking problem, which also does the same thing, but with an approximation. So which means that it doesn't work as well. Although with ImageNet, we were only 6% away from like the best backprop run with this approximation. Okay, so that's all I have. So just to kind of summarize, I think the next epoch of scaling will be based on more scalable algorithms and also hardware algorithm co-design and architectural exploration. This requires a top-down approach to think about what algorithms we need from first principles. And asynchronous and distributed algorithms are a promising approach to do this with a lot of interesting and challenging open questions. So this is like, all of this work is done with like a huge group of collaborators from Rube and Bielefeld and Dresden and Bits, Pilani and all that. So there's like a lot of people involved in this.